So we have Dr. Krishnendu Haldar, who's an assistant professor in aerospace engineering at the Indian Institute of Technology, Bombay, which means that while it's 2 p.m. here, it's 2:30 a.m. His time. So
Yeah.
we appreciate you being here and live. So his talk today he'll talk about polymers infused with magnetic particles and how you could change the characteristics of the properties of that material and models for how that behaves. So welcome, Dr. Haldar, and you have the floor.
Okay, thank you very much for your kind introduction. So good afternoon to all and very good morning from my side. So I am Krishnendu, and today I will be talking about a part of my research focusing on this title, Magnetomechanics Modeling of Magneto-Active Polymers. So this is again a vast area. However, I will be mostly focusing on the modeling side of this Magneto-Active polymers, some experiments, but I do not do experiments by myself. So I borrow data from others. So and then I interpret those data to fit the model parameters. So the outline of the talk is kind of like this. I will briefly introduce with you this material, Magneto-Active polymers. Then I will briefly discuss the Magnetomechanics, or how to model or one approach of modeling of such magnetomechanics involved with this polymer deformation, both in terms of magnetic field as well as mechanical forces. Then some experimental description to characterize such polymer system, and then I will also describe how to identify parameters and the challenges for magnetic materials to parameter identification. Finally, some model predictions, and I hope I will have some time, and then I will discuss this finite element analysis of magnetomechanics based on the developed constitutive response. So this is the way I want to introduce this material. So here, the top left corner is a schematic of RVE of this material. So the cube thing is your polymer matrix, and what happens, you have a tiny magnetic filler particles, and the way it is cured, that this polymer makes a good bonding with these filler particles. So when you apply magnetic field, so all the magnetic particles, they get magnetized and they try to be aligned with the applied magnetic field. For this case, B here, or you can apply field along this direction. And once you do that, you generally observe these two fundamental changes. One, the material starts deforming, as well as you have some sort of tunability property in the stiffness, as well as the damping properties. The damping properties coming as this is the polymer matrix is viscoelastic. And on the top of that, through this magnetic particle or magnetic fillets, you are also getting the magnetic characterization of this material system. So depending on how you are curing, you can end up with your final configuration of magneto-active polymers, that your magnetic fillers are evenly dispersed in the polymer matrix. So you can think about this as an isotropic condition, and it may happen during the curing time. You are applying magnetic field in a particular direction. For example, though you are applying magnetic field here in, when you have already cured material, but during the curing process, what you did, you were applying a magnetic field along the direction of the chain, so that all these tiny field particles, they got aligned, and during the curing process, you get a nice chain out of there. Once you have these things, you have a very strong anisotropic property, mechanical as well as your magnetic anisotropic properties are observed for magneto-active polymers. So few applications of such a material system, obviously, you can see that you can control the stiffness as well as the damping property. So the stiffness is controlled, as you can imagine, that when you are applying magnetic field, the interaction between particular or interfiller attraction, they becomes very strong, and that's why the overall response becomes very stiff. And similarly, the stiffness changes the way you are getting cured. That means whether you have isotropic system or anisotropic system, but the bottom line is that you do observe a strong change in stiffness, as well as it influences on the viscous property. So you can use these with the devices that you are interested to change the stiffness or damping properties at some very quick instance of time. It could be used in miniature sensors, actuators, soft robotics, some soft biomedical applications, and so on. So this is the microstructural perspective of this material, and let's see how this material behaves phenomenologically. So here in the left-hand side, this diagram, the schematic diagram, is presenting how you are doing testing. So this is your testing specimen with this Magneto-Active polymers, and you are applying a magnetic field in a specific direction. In this particular study, actually, we are considering your applied traction and the direction of the applied magnetic field. They are aligned. And when you perform testing, the mechanical testing at different magnetic field, this is the experimental responses you receive from your testing machine, that when you are increasing the magnetic intensity, like this blue line is for H equal to 0, and then you keep on increasing up to almost 0.5 Tesla, you clearly see your stiffness is changing as well as the hysteresis loop is changing. So it is in phenomenologically, you clearly observe this very, strong or very prominent changes. So the key features are the slope is changing. That means you are tuning your elasticity of the polymer system. You are changing the hysteresis. It also influences the directionality, and it also depends on the magnetic rate as well as your stretching rate or the mechanical rate. However, I didn't present any rate dependent figures here to motivate you, but this is just a motivating slide. That's what we generally observe for such material in a magnetomechanical testing condition. Now the point is, if we are given such responses, how to model that such that as a prediction you will be able to capture these salient features, and that is a kind of the main objective, to develop a constitutive equation for such materials which are very much elegant to produce a prominent responses at different magnetic fields. So now I am gradually entering to the modeling part. So before going there, what I like to introduce all the associated variables used in the modeling. So this is a continuum based modeling. So you are familiar with these potatoes. So at t equal to 0, you have this configuration. So most of the capital letters are used for the field variables at t equal to 0 or in the reference configuration, and you have this deformation map chi, and at t you have this deformed configuration where this particle at p position at point p moves at point p prime with this small x displacement vector, or rather position vector here. Our rest frame variables for these magnetic materials are the magnetic induction B, the magnetic field H, and magnetization. So these three variables we are considering, and as this is a purely magnetic, we are not considering any electrical variable at all. So these are all rest frame variables, but as like one of the major applications here for actuation and like or sensor, it's more likely that when it undergoes a deformation, whether this is under applied magnetic field or mechanical load, you can think about the velocity at each point is not at all negligible. If so, instead of these rest frame variables, we consider the moving frame electromagnetic variables. So this is just like a kind of a change in frame. And in the moving frame, which is more suitable when we have a motion of such a MAP system or magneto-active polymer system, then this tilde denotes your moving frame variables. However, we are considering the velocity x dot is way less than the velocity of the light. In that scenario, you just have b tilde equal to b, h tilde equal to h, m tilde equal to m. However, the catch is this will generate, or the velocity will generate an electric field, though we are not at all considering any sort of electrical interaction here. However, whenever it has some velocities, and when the velocity at each point is interacting with the magnetic flux environment, it will generate a electric field. And this is the constitutive equation, the standard constitutive equation connecting B, the magnetic flux and magnetic field, with magnetization M. Okay, that's it. Now the very next thing is, okay, what are the associated field equations for such material system? Obviously, as we are talking about coupling, we need to satisfy our electrical field equations, which are nothing but the Maxwell's equations. So we have everything here in the deformed configuration, like omega t. So we have the Gauss law, divergence B equal to 0. We have Ampere's law, curl H equal to 0, and Faraday's law exists here because we have this little guy E tilde there is generated out of the motion of the at each material points, and this B star is nothing but the convected derivative. And for the mechanical equations, we have, as usual, our standard conservation of mass, your linear momentum, conservation of linear momentum, and conservation of angular momentum, which gives the symmetry of the Cauchy stress. So sigma is the definition of Cauchy stress, because as we are working with a finite deformation problem, we have a different definition of stresses for here at omega t. This is true for the Cauchy stress. So these are with the field equation. Then the next important thing is the conservation of energy. So this is all kind of, it looks similar the way we have mechanical conservation of energy, but couple of changes. One, we have a magnetic energy here, which is m dot b dot. It represents the interaction with the magnetic energy. And another thing is, in general, we have the Cauchy stress contracted with your velocity gradient, which is capital L for your stress energy. But here you'll see this is sigma L prime. So with a consistent calculation, you can show that sigma L prime is nothing but your Cauchy stress minus the Maxwell stress. It automatically takes care of with some consistent. This is very straightforward, but I'm giving you the final result. And this Maxwell stress, or the stress generated by this magnetic field, takes this following form. So the work conjugate is like the Cauchy stress. So Cauchy stress is for I mean, this coupled problem, you are not at all distinguish whether this is like a purely elastic or purely viscoelastic or purely magnetic. Is the total effect, the overall effect of the system, the way it behaves. However, with some consistent way of, after some calculations, you can automatically get that your magnetic stress or your Maxwell stress is just subtracted from your total stress, and you get the leftover, which is the work conjugate of your strain rate or this velocity gradient. And finally, you have this entropy inequality. So that's all we have, all our field equations. So the next thing is direct, that the whole idea is to propose an energy function such that when you derive your constitutive responses from this energy function, you will get your magneto-active polymer responses close to the experimental responses. That's the target. So the whole idea is how good one can propose an energy function. So this is a standard practice. So for the polymer, we are assuming this is like a, compressible. So you decompose first your deformation gradient like a volumetric part and this isochoric part. So if bar, everything is bar is related with this, isochoric part. So you take the determinant of a bar, you will get 1. And now you are also doing in the finite viscoelastic setup, you are decomposing your F an elastic part and viscoelastic part. So basically, in continuum scale, if you think about like a Maxwell elements in a spring dashpot system, so it could be shown that in a continuum setup, it can nicely fit to this multiplicative decomposition of an elastic part. So this is your spring and this is your dashpot system, and alpha is the number of Maxwell elements you want to consider. So this is again a standard practice, is nothing new here. And then you are defining your left Cauchy strain or deformation tensor like C bar with F bar, and you identify one of your internal variables. So this is one possibility to set the CV alpha or the viscous deformation related to your viscous part of your Maxwell elements as one of your internal variables. So this is a phenomenological modeling and internal variable approach. We have state variables and the way we identify. So there are other possibilities, but here we identify our internal variables with the CV alpha with this thing. And so we are writing our total energy density as like the volumetric part. We have this total elastic part, which is only the function of C bar, some magnetoelastic part. So we have only the deformation and H coupling, some function, so that we like to propose. Then we have a pure magnetic part. Now we are entering to this magneto-viscoelastic. Again, I'm splitting it in 2 parts. One is like pure viscoelastic. So you see there is no argument with H, is only C, and now internal variable comes into play, this viscous part. And also we have this magneto-viscoelasticity with CV alpha H. So this is the proposed functional from that, what sort of energies we want to consider to model such a magneto-active polymer responses. And then you go for your standard procedure, and if you just include the free space energy, which looks like in this particular format, and actually if you take this equation only with this free equation, free energy, you will get basically the Maxwell stress back, this guy. So that's why you include your free energy. So your total energy is like the material energy and the free space energy that the material is occupying. And if you do that, you get directly the total Euler-Kirchhoff 2 or PK2 type of stress S, your magnetic induction B, and your second law inequality or the Clausius. You have inequality, you have this left over there. Now, as this is a dissipative system and we are going an internal variable approach, so there are evolution equations of CV alpha, your internal variables, and which one possible form is the way we are presenting here. So I'll discuss a little bit detail about this particular form, and obviously there are other possibilities of expressing your evolution equation. And this is nothing but your like a Mandel type of stress tensor. Okay, now the point is, okay, we have everything in terms of functional form. So what type of function we can select to represent these MAP responses? So these are the invariants we are playing with from I1, I2, I3, or which is J here, root over I3, which is standard. And we are introducing this I4, I5, I6, where I4 is a pure magnetic invariant, and your I5 and I6 are the invariants associated or coupling with this kinematic quantity C bar. And so we will be trying to have our explicit energy functional form with these invariants. So the elastic energy is a standard Moni-Rivlin form. Is nothing new here. Now, what we did for this magnetoelastic energy, we just playing with if we can make this coefficient as a field dependent, and that's what we are doing here. Simple extension from like elastic energy to magnetoelastic energy, and for the time being, we just consider C1 equal to 0. It works, so that's why we stick to C1 0. If it doesn't work, then somebody again come back and try to manipulate what should be the best function for this predicting MAP or map responses. So from magnetoelastic energy, the catch is only we are making the coefficient field dependent, and we are selecting this function such that it saturates with magnetic field. So if you keep on increasing your magnetic field, at some point it becomes asymptotic with a predefined value, and all these values are experimentally motivated. And for viscoelastic energy, this is just like your new Hookean type simple form. And for magneto-viscous elastic, we are just playing with again with this coefficient, which is constant for normal viscoelastic, and we are just making that coefficient field dependent. Again, we are using, after many trial and error, we found, okay, this tan inverse function, it works well, and it takes the saturation effect pretty decently. So that's why we stick to this particular form. The whole idea is kind of like an asymptotic function after some critical value of h. And you have pure magnetic energy. And for the evolution equation, we again have a coupling in the evolution equation, and this is a standard procedure to get the evolution equation, which is proportional to the derivative of some predefined function. And for this case, we just took the norm of this deviatoric part of this Mandel stress. So this is a form, not the form. There are, depending on the problem, you can come up with like more sophisticated version, but somehow whatever target we have, this form is working. So we just stick to this particular form. And now we are expressing our stress components. So these stress components we are getting here. So once we know this, our energy function, we know the S, but this is PK2. Now what we are doing, we are just switching from PK2 to PQ1. The reason is that whatever experimental data we have, that is the way it is measured, that you are considering your original cross-section area A0, and during the deformation, you are measuring your traction force in a deformed configuration. So this is by default, your stress measure is like the traction at the deformed configuration, or the force in the deformed configuration over your undeformed area. So that gives you actually PK1, or this total or the Euler stress here. And if we convert everything, then we can interpret the experimental data directly. So that's the motivation why we are moving again from PK2 to PK1 format. And similarly, we have this magneto stress in this particular form. Okay. So now let's go to the experiment. that how. So this is taken from this Hitmer et al. So this is in Austria, Linz, this Institute of Polymer Technology, where this collaboration was there for the experimental part. So what they did, so this is the specimen here, and what you see here, this circle, they are the cross section of a cylindrical permanent magnet. So you can imagine in the z direction or in the out of plane direction, you have a cylindrical rod, and in the cylindrical magnet or in the permanent magnet, you have the direction of magnetization along in the diametrical direction. So this particular arrangement, so for this case, you have like 6 such permanent magnet or cylindrical rods, which has a specific orientation of magnetization. And you can show that for this particular Hallback array arrangement, you will be producing an uniform field inside, which is along the direction of applied force. And if you rotate this angle, you'll be able to change the direction of H. So that's the this is what I mean. So this is your initial configuration. So this is like 30 degree we started with, and you are getting an uniform magnetic field along the direction, in the vertical direction. Now if you rotate, or if you start rotating the equal angle in each cylinders in this particular Hallback array format, you will be able to rotate the direction of magnetic field in a clockwise. So you move anti-clockwise here, and you move your magnetic field inside in the clockwise direction, and that's what you are seeing here. So at some intermediate angle from 0 to between 0 to 90 degree, you are able to incline your direction of your magnetic field. And another extreme position is you rotate fully 90 degree, and you rotate again your applied magnetic field direction from vertical to horizontal, a full 90 degree clockwise change. So this is very useful where you want to test, or you want to change your field to test the anisotropy of the system. That's why they adopted this Hallback array. But only one disadvantage is you cannot increase the field as all of them are permanent magnet. So that's why they have this 0.43 Tesla magnetic field generated uniformly inside this free space, but that is fixed, you cannot change. But what you can do, you can change the direction. So that's the big advantage. Most of the time when you work with permanent magnets, the electromagnets, you can change the intensity, but changing direction is very tricky. So however, so now you do all your mechanical testing. So as our case is like this one, so this is the case we are interested in, that your magnetic field is aligned with the direction of the applied force or applied stress. So this is a stretch controlled experiment. So we take the stretch lambda along the E1 direction, where E1 is the vertical, the direction of the loading. And we are considering this is an isochoric stretching, so that bar part is gone because data for j equal to 1. And we are expressing our this viscous element in terms of this lambda v alpha, where this is the unknown. So that's you do not know, but you know this lambda from the stretching. So that's why in 1D you reduce your system with this ODEs, but one algebraic equation. So that's why you are basically solving a differential algebraic equation. And MATLAB, you can easily solve this setup or this format there. So this is what your input, your lambda dot as a given rate, you are doing the stretching. This is the evolution equation. You start with some known value, which is like 111, because in the undeformed configuration is nothing deformed, and then you let it evolve the way you proposed your evolution equation. And again, you can control it with a given magnetic field, and you have your constitutive responses with respect to P as well as M. But I am so the way it takes DA system, like you can I mean, is easier to handle with one algebraic equation. So I just put the magnetic constitutive equation in a red form. So that's all you have, and you are ready to calibrate your model parameters. And this table shows what are the model parameters associated. So this C1, C2 was like the monodivlin one, pure elastic, then magnetoelastic, viscoelastic, magneto-viscoelastic, and magnetic. So these are the categories of parameters we have. Now let's see how we can excuse me, calibrate all these parameters. But before going, for parameter identification, one thing, I mean, we considered here the demagnetization effect. So that is a really very, I mean, annoying thing for magnetic material. So the point is, whenever you, so our Hallberg array, it produces uniform magnetic field inside the space what we are considering here. But once you put this magnetic material as it becomes magnetized, it will have its own magnetic field, which is known as the stray field. So what you are recording as your magnetic field, like 0.43 Tesla, that is your applied magnetic field, but which is not true, which is not actual magnetic field inside any material point, because it will change due to the demagnetization effect. So that's why. So this is HA, is the applied magnetic field through this Hallberg array in this particular case. And this is true for any, it doesn't matter whether you are applying this field with Hallberg array or with permanent magnet or with electromagnet, is always there. And most of the time, if your specimen or material is strongly magnetized, your stray field or this demagnetization field is very strong. So this H is actually the field you are experiencing inside the material, and that H should involve with the constitutive response. Then it will present the true constitutive or the material response of the I mean, magneto-active polymers or whatever magnetic system you are working with. So we know HA, which is applied from this Hallberg array, but this HD field you compute with this demagnetization factor, which is available. I mean, even for the cylindrical case, which is like our case here, is like a dog bone specimen. We're just eliminating the effect of the two ends, and we are just considering our, okay, I think I can. So we're just considering this cylindrical effect there. And this D is available for this particular geometry. And this is what we got after this demagnetization correction, that it shifts quite like in a like a very prominent way from the experimental fitting. And the way we're correcting, solving this whole bunch of coupled equations, and we got the correction. So once we have this corrected value of MH relation, then we are going next to calibrate our other parameters. So we have now a corrected parameters for magnetization responses. So next, what we are doing a purely mechanical testing, simply elastical, I mean, nonlinear elastic response for this material. The idea is the rate is considered is very slow, such that you can discard the viscous effect. So all the viscous energy or viscous contribution to the stress part is neglected. This is the actually specimen geometry, 27 millimeter height. The material is EcoFlex. So this is a commercial name, but this is like a very rubber-like soft material. and the iron feather is 10% volume fraction, uncoated spherical, and the mean size is around 5 micron. Now, once you calibrated your material parameters from this elastic response, the next thing is you are just switching on your magnetic field, which is 0.43 Tesla. Knowing the value of the elastic constant or Muller-Evelyn constant with no field on the top of that, now you calculate your magnetic coefficient. So you are done with elastic and magnetoelastic. And same thing you are repeating with a relaxation test, so that you are extracting your viscous parameters from like a pure viscoelastic test. Then you switch on your magnetic field, which is 0.43 Tesla, this applied magnetic field, and somehow you are correct. As you got your corrected magnetization response, you have a way how to connect the applied magnetic field to the actual magnetic field inside the material, and you get your magnetoviscous parameters. And then we are done. So in this table, whatever parameters are there, these are the sufficient experiments to calibrate all the categories. And this is the model prediction here. So this is a cyclic response, and we only have our data to compare where there are no data used for this particular experiment. So this is a pure prediction. So all the calibration are done from these experiments, like 1 to 6 experiments, no 5 experiments, and then we are actually predicting how good or how bad our model could match with the actual experiment response of the cyclic loading. And here is like if you keep on increasing, so this is the model prediction. Now if you keep on increasing like up to 1 Tesla, how you will generate your material responses. Okay, so the next thing is we are just kind of playing with whether it can capture the different stretch rates and different like a field rates. We wish we have more experiments to compare, but unfortunately we do not have any experimental data to compare with. But however, we're just checking if the model at least can distinguish that now you have a different stretch rates or field rates. Yeah, so the next thing is this coupled finite element analysis. So what we are, I think I have like 5 more minutes, right? It will be fine. So I can wrap it up within 5 minutes. So these are your magnetic system field equations. So we are going for like a potential approach. So the H vector could be expressed as a gradient of a scalar. So this phi is a scalar potential. And once you do that, you can actually trivially satisfying your Gauss-Fadde law or divergence of B equal to 0. This is the constitutive response that we just calibrated from the experiment. So this is coming from the modeling, and the rest of the things are like a standard. You have Dirichlet boundary condition and Neumann boundary condition, and same thing for. So here is the coupling. So you see your deformation gradient is sitting here. So your electrical or magnetic system is already coupled with your mechanical system, and along the same line, your constitutive relation, the mechanical constitutive relation, you have this H sitting. So you have now, even to solve this boundary value problem, everything is coupled there. So that's the way. This is a standard procedure. So I can probably skip this thing very quickly. So from the strong form, you just multiply with this test function and integration by parts, blah blah blah, standard procedures. You get your weak form for the magnetic system, weak form for the mechanical system. You discretize your system, and then you get your elemental residuum for magnetic as well as your mechanical cases. Then you linearize the system, and directly you will get all your coupled elemental stiffness matrices is there. So this coupling with magnetic field with mechanical, this is like field. This is again mechanical field, and this is sorry, mechanical PF. Both are mechanical, purely mechanical, and this is mechanical coupling with your magnetic field. So you get your coupled stiffness matrix. Then you go for assembly, and you will get, you are ready to run your FE code. So we use for this problem this PIP open source finite element software, and nodal degree of freedom is 3 for the mechanical and 1 for the scalar magnetic potential, which is phi. And this is just to test the problem or the constitutive response that we developed, that how it works in the nonlinear coupled FE setup. It's just a plate with a hole, and it's a good problem to test with, because if you have singularity issue and all these things, it can nicely give you a very good indication that your code is not running or is failing. So there's the motivation why we selected this problem. So this is one simulation. So the boundary condition is the bottom face is rigidly fixed, and you are applying a shear on the top surface, and you get this deformation. Now the very next step, you are just now switching on your magnetic field. So the way you are applying a scalar potential between this top and bottom surface, such that it creates a magnetic field around 0.75 Tesla. And the mechanical boundary conditions are the same, that the bottom surface is fixed, and you are applying a shear load on the same shear load on the top surface, and you can see that, I mean, the final configuration is way different what we have observed with no field. So it is basically capturing that material becomes now stiffer due to this applied magnetic field. And here you have this, like when this is deforming, how this magnetic flux Bx and By are changing. So it's a mechanical deformation, and the map is with your magnetic flux Bx component and By component, the same problem. I think that's all we have. I think I am within the time. So that's it. Thank you very much for your attention, and I think it's open for questions.
Right. Thank you, Dr. Haldar. Let's give him a round of applause. And there's
Yeah,
certainly,
thank you very much. Yeah.
And there's
Thank
certainly time for questions. So if you have a question, unmute yourself and ask away, or type it in the chat. Thank you.
Yeah.
Hey, Krishnendu, I have a question.
Yeah, Nick. Yeah.
Hey, so if you were going to try and model this behavior in 1D, how would you account for the demagnetizing energy? I guess, I mean, it's not necessarily only for this model, but just any sort of...
No, you are right. So in 1D, I believe, in principle, there is great difficulties to reduce the problem in 1D. But however, what you'll be actually, in 1D, actually, through the theoretical computation, there is no way you can compute demagnetization effect. So the way I believe, you can take the actual dimension, which is 3D, and then you can compute your demagnetization factor and apply the other 1D activities is there. So that's the way I think this problem.
I see. So it'd be kind of like iterative. You'd need to know.
Yes, because 1D is sometimes 3D is easier. When you want to reduce everything in 1D, there are many, like some inconsistent effects pops up immediately. So that's really annoying. So that's one of the thing that in 1D, in principle, there is no demag effect, but here you just consider this is cylinder and take the dimension, and you get the demagnetization effect for a cylindrical body, and you just apply the rest of the 1D condition.
Thank you. And also just one more question. What is the sort of the magneto stress of this stuff? Like, what is this material exactly? And will that stress saturate eventually with field, like a blocking stress or something?
This stress is kind of like whenever you are applying some, so if this is the material and if kind of this is the ambience of some magnetic field. So magnetostress is, I mean, you can think about as, so for this material system, as we have like magnetic fields, they started interacting each other. So naturally the body will be getting stress inside whenever you are switching on your magnetic field. So they are kind of inherently generating a stress condition inside the body, and that this magnetostress or Maxwell stress will take care of that stressing effect.
And will that saturate eventually? I mean, once
eventually, I mean, if we go here, unfortunately, magnetostress is so here you can keep on increasing age, so it is indeed not saturating at all. So more, if you keep on increasing field, I mean, you will get it more stressed. But the best way, I mean, I just like if we have a valid or very good experimental paper that they are demonstrating the magnetostress, but still it's not there like in a satisfactory way. So this is, for me, this is kind of like an open question to verify it experimentally.
I see.
That how is a very interesting thing. Exactly. Yeah. Go on.
Is this a specific material? What polymer is this with? I think you said it had iron particles or.
Yeah, this is EcoFlex polymer. So this is a commercial name though. So I actually, one minute. So so when I touch the material, this is like really very soft rubber like. And yeah, iron particle, they are like a 10% filler. So I think they moved up to, so all this experiment, this Hipman et al., they did in Austria in this Polymer Institute, and I visited once there. So I had some scope to even touch their material and see their testing system. So it's very soft rubber like.
Cool. Okay, thank you.
Yeah, you're welcome, Nick.
Yeah, thank you for the question. Maybe one more question, time for one more question.
Sure.
If you have a question, type it in the chat or unmute yourself and ask away.
Yeah, or feel free to contact me if you have some questions or if you have some better idea of doing these things. I'll be happy to collaborate, or that's perfectly fine. It's not at all a problem.
All right, so maybe this is a good place to end. Let's thank Dr. Haldar for his time.
Thank you very much. Yeah.
Right, and if you want his contact information, you could certainly contact me or talk to Dr. Bruno. So thanks again. Thank you everyone for joining us.
My pleasure.
This week. Thank you, Dr. Haldar.
Thank you very much.
All right, thank you.
Yeah, I appreciate it. Yeah, it's my pleasure to